So I've drawn a picture of what's going on. In the before picture, you have two protons that are close together. The distance is given in the question there. You're going to start them at rest and let go. They're going to repel each other. So they're going to speed up, pushing away from each other. That means they're going to increase in kinetic energy. And if they increase in kinetic energy, that means their potential energy is going down. It's a transformation of energy. And the after picture shows the two protons very far away. And the hint given was to see the bullet in slide 2 of the notes. And it says in that bullet that when the point charges are really far away, that the potential energy is essentially zero. Because potential energy has a r, a distance in the denominator. So if they're very far away, you make the denominator really, really large, the fraction will pretty much equal to 0. Okay, so we'll solve this with the conservation of mechanical energy. So starting mechanical energy will equal ending mechanical energy. Where the potential energy here actually refers to electric potential energy. There's one important assumption to make, and you can make it, is that gravitational potential energy is negligible. You can confirm this assumption for yourself if you've got the time. You can calculate the gravitational potential energy between these two protons by using the masses of the protons. And when you calculate it, you'll find that it has significantly less energy versus the electric potential energy. So it's going to be negligible. Okay, so back to our conservation of energy. There's 4 terms there. A couple of them end up being 0. So the starting kinetic energy is 0 because they start at rest. Both of them start at rest. And the final potential energy is going to be 0, as discussed earlier. When they are very far away, the potential energy is basically 0. So we basically have the starting electric potential energy. All of it is going to get transformed into kinetic energy, and we're going to solve for the speed of these particles. So the potential energy, the formula is K QQ. I'm going to call them Q1 and Q2. Well, they're both protons, so they're going to be the same value, over R1, the distance separating 1. Actually, since the two Q's are the same charge, they're both protons, I'm just going to replace Q times Q with Q squared. And that's going to equal to the kinetic energy. Now, both particles have kinetic energy. Both protons have kinetic energy. So while the kinetic energy formula is half mv squared, that stands for the kinetic energy of one of the protons. I'm going to multiply that by 2 because we actually have 2 protons. And due to symmetry, they're going to be moving at the same speed. So they're going to have the same kinetic energy at the end here. So I multiply half mv squared by 2 because there are 2 protons moving at the same speed. The half and the 2, half times 2, just makes 1. So that simplifies the formula a little bit. We're going to isolate this for the speed. So we'll divide by the mass and we'll square root. Which, before I plug in the numbers, I'll simplify it a little bit. The square root of q squared is just q. So I'll take that out of the root, but I have to leave the k over m inside. Okay, so that's what I will type into my calculator. So put in the values. The charge of a proton is known, 1.60 times 10 to the negative 19 coulombs, times the square root of Coulomb's constant. I'll do it to 3 sig figs, so 8.99 times 10 to the 9, and then divided by the mass of a proton, 1.67 times 10 to the negative 27. Yeah, you're going to have to use the useful values there. I'm missing something. Yeah, let's make this correction here. I forgot about this R value here. It just kind of disappeared in my algebra. Let me fix that. It ends up in the denominator here. So that's why it's better to rearrange equations first before putting in numbers, because if you catch an error like this, it's more easily fixable. I'll put in the distance that we're given, 1.0 times 10 to the negative 14. Okay, so that's all going in the calculator. I'm going to get a speed out of this, and I'm really hoping that this is less than the speed of light. So let's see. Okay, so I end up with 3.7 times 10 to the 6, which is less than the speed of light. It's just about 1% of the speed of light, actually. This should be the 2 sig figs because of the 1.0. And that's the answer.